Okay, in this video we are going to look at some properties of m-ary trees. So first property is about counting the vertices in a full m-ary tree. So the statement reads as follows: a full m-ary tree with I internal vertices contains mi plus 1 vertices. Okay, so let's look at an example, then after that we will go and prove the statement. So here if you look into this particular tree, we can see that number of internal vertices I is equal to 1, 2, 3, 4, and the statement says then, okay, so here we can see that this tree is, it's a full, okay, it's a full 3-array tree. Okay, so m is equal to 3 here. Okay, so that says number of vertices is equal to 3 times 4 plus 1, it is equal to 30. Okay, so let's see whether that holds for this tree or not. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so we can see that this particular result, it holds for this tree, and it's a full 3-array tree. Okay, so let's go and prove the general case. A full m-ary tree with I internal vertices contains mi plus 1 vertices. Okay, so let's prove this statement. Okay, so here we can see that, okay, if you look into this particular tree, okay, each vertex in this tree other than the root, okay, is the child of a unique vertex. Okay, so keeping that in mind, okay, let's go and prove this particular statement. Okay, so you can see that each vertex in tree T, okay, suppose that we have, in a full m-ary tree, other than the root is the child of, okay, it's a child of a unique vertex. Okay, so it's a child of its parent. Okay, so here we can see that if you look here, it's a child of this vertex, a unique one. So similarly, if you look here, so this particular node is a child of this one, and the parent, this is a unique vertex. Okay, so that is true for every vertex other than the root. Okay, and again we can see that each of the I internal nodes has m children, because we are dealing with a full m-ary tree. Okay, so each of the I internal vertex has m children. Okay, and that says, so there are a total of mi children. Okay, so taking this coordinate and adding the root node, we get the result mi plus 1. Okay, so adding the one, okay, non-child vertex, in this case the root, root. Okay, we have n equal to mi. Okay, mi from here plus 1. Okay, and that's the proof. Okay, so here each vertex in a full m-ary tree other than the root is the child of a unique vertex. So, and each of the internal vertex has m children, so we have a total of mi children. So okay, it does not include the root node. Adding the one non-child vertex, the root, we get the result. Okay, n equal to mi plus 1. Okay, so that says this statement is true for any full m-ary tree. Okay. So let's go and show some statements that follow from this particular statement. Okay, so the first statement says a full, again we are dealing with a full m-ary tree with n vertices. We have the number of internal vertices is n minus 1 divided by m, and the number of leaves L is n minus 1 times n plus 1 divided by m. Okay, so okay, let's see whether this holds for this one or not. So here if you look into this particular tree, here we can see that number of internal vertices is 13, and not number of internal vertices, number of vertices is 13. Okay, and here this is a 3-array tree. Okay, so number of vertices 1, 2, 3, 5, 6, 7, 8, 9, 10, 13, and it is a 3-array tree, and that says the number of internal vertices is, if you believe in this particular statement, that is okay, it will be like 13 minus 1 divided by 3. Okay, that is 12 divided by 3, which is equal to 4. Okay, so let's count the number of internal vertices: 1, 2, 3, 4. Okay, so this particular thing holds for this tree. Okay, it's a okay, again we can see that it is a full 3-array tree. Okay, if the tree is not full, then it might not hold. Okay, so let's find the number of leaves. So we use this equation. So that says okay, m minus 1 is 2. Okay, 2 times 13 plus 1 divided by 3. Okay, that is 26. 27 divided by 3, which is equal to 9. Okay, so let's see whether this tree has 9 leaf nodes or not. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so for this particular tree, this result holds. Okay, so here the important thing about this statement is that if you are given the number of vertices in a full m-ary tree, okay, we can find the number of internal vertices and the number of leaves using okay these two equations. Okay, so let's go and prove this one. The proof is just algebra. Okay, so from this statement we have n equal to mi plus 1, okay, where n is the number of vertices and I is the number of internal vertices. Okay, so we use that for solving for I here, right? So from that result we know n equal to mi plus 1, and solving for I we get I equal to n minus 1 divided by m. Okay, so we proved this part, and here okay we have this condition: the total number of vertices is equal to the total number of internal vertices plus the total number of leaves. Okay, so from this thing we can find the total number of leaves by using this identity. Okay, number of n minus I, and okay, so let's substitute this I here. We get n minus 1 divided by m. Okay, and that says this is equal to mn minus n plus 1 divided by m. Okay, and taking this common factor n, we get m minus 1 times n plus 1 divided by m. Okay, so we proved this also. Okay, so if you know the number of vertices in a full m-ary tree, then we can find the total number of internal nodes and the leaves using these two equations. Okay, so let's look into some more properties. So this says in a full m-ary tree with I internal vertices has mi plus 1 vertices and m minus 1i plus 1 leaves. So here the important thing about this statement is that if you are given the number of internal vertices in a full m-ary tree, then we can find the number of vertices and the total number of leaves, okay, in that tree. So let's look at this example. Okay, so here the total number of internal vertices is 1, 2, 3, 4. Okay, so and here again it's a full 3-array tree, so m is equal to 3 here. Okay, so let's find n. So that is going to be 4 times 3, okay, or maybe 3 times 4 plus 1, that is 30. Okay, and if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30. Okay, we can see that that's correct for this particular tree. Okay, so let's count the number of leaves. So m is 3, so m minus 1 is 2. Okay, 2 times 4, that 4 is the number of internal vertices plus 1. Okay, that's 8 plus 1, 9. Okay, so let's count the number of leaves. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so for this tree, okay, which is a full 3-array tree, okay, this statement holds. So let's go and prove for general tree. Okay, so the first part we already proved. So if I use the number of internal vertices, then we have this result. Okay, so we proved that here. Okay, so let's go and prove the second part. So again we are going to use this identity. So n is equal to total number of internal vertices plus total number of leaves. Okay, from this we can see that total number of leaves is equal to n minus I. Okay, so we know n is equal to mi plus 1. So substituting that here, we get mi plus 1 minus I. Okay, and here taking this common factor I, we get m minus 1 times I plus 1. Okay, so we prove these two. So that says if we are given the number of internal vertices in a full m-ary tree, okay, we can find the number of vertices and number of leaves using these two equations. Okay, so let's look into one more property. So this says, okay, a full m-ary tree with L leaves has ml minus 1 divided by m minus 1 vertices and L minus 1 divided by m minus 1 internal vertices. And here again the application of this is, if you are given that there are L leaves in a full m-ary tree, then you can find the number of vertices and number of internal vertices using these two equations. Okay, so let's see whether this statement holds for this full 3-array tree. So here the total number of leaves is 9. 3, 4, 5, 6, 7, 8, 9. Okay, so let's find this n, and here this is a full m-ary tree, so m is equal to 3 here. So m into m into L minus 1 divided by 2, 3 minus 1, 27, 26 divided by 2, which is equal to 30. And we saw this particular tree has 13 vertices. Okay, so this tree satisfies this equation, and let's find the number of internal vertices. Okay, number of internal vertices is, using this equation we get 9, n equal to 9, 9 minus 1 is 8, 8 divided by m minus 1, which is equal to 4. Okay, so here we can see that internal vertices, total number of internal vertices 1, 2, 3, 4. Okay, so this equation do satisfy for this tree, and let's go and prove for general case. Okay, so here we are given the leaves, number of leaves, and we want to find the total number of vertices and total number of internal vertices. Okay, so here we have this relation. Total number of vertices is total number of internal vertices plus total number of leaves. Okay, so from the previous one, okay, we know this equation, right? I equal to n minus 1 divided by L. Okay, so let's substitute that here. After that here we get n minus 1 divided by m plus L, and here cross multiplying we get ml plus n minus 1 divided by m. Okay, and multiplying both sides by m we get mn equal to ml plus n minus 1. Okay, and moving this to the left hand side, so we are looking for n, right? So let's move this to the left hand side. We get mn minus n equal to ml minus 1. Okay, so taking common n we get m minus 1 times n equal to ml minus 1, and solving for n we get ml minus 1 divided by n minus 1. Okay, so we have this equation. Okay, so let's go and prove the other one. Total number of internal vertices is L minus 1 divided by n minus 1. Okay, so from here we know I is equal to total number of vertices minus total number of leaves. Okay, and we all found n here, so let's substitute that here. So n is nothing but ml minus 1 divided by n minus 1 minus l. Okay, so this is equal to ml minus 1 minus ml. Okay, and we have minus 1 minus l, so we get plus l. Okay, so this will cancel. Okay, so this will cancel, and we have this m minus 1 in the denominator. Okay, so rearranging this we get L minus 1 divided by m minus 1. Okay, so that agree with this equation. Okay, so that's the proof. So in the next video we continue with some more properties of m-ary trees.